Okay, so now I'm going to give you this example. And I think this example is probably kind of more characteristic to overuse that word of things that exist in real life rather than some of the things that we've seen so far. And I'll explain what that means in just a moment. So we have this, or I'll explain what I mean by that in just a moment. So we have this PDE, the t derivative of u plus u times the x derivative of u is equal to 0, and we have u of x 0 is equal to 1 over 1 plus x for x greater than 0, and then u of 0t is equal to 1 for t greater than 0. Sorry, thought I put my phone on mute. Okay, so now our Cauchy curve, similar to things we've seen before, is the positive x-axis and the positive t-axis. So the thing that I want to point out here is that our initial data, it's continuous on the positive x and positive t-axis. So we have continuous data here, but what we're going to see is that there's still going to be a shock forming. So this is different than any PDE that we've seen so far. Up until now, all of the PDEs that we have seen have, the solutions have been at least as regular as the initial data. So if you think way back to the diffusion equation, we actually could take our initial data as being a Dirac delta distribution, and for all positive t value, we had an infinitely smooth solution. If you looked at the wave equation, whatever regularity we started out with in the initial data, we got a solution that was just as regular as that in the solution. So if we started with a continuous function, we got a continuous function as the solution. If we had a differentiable function, we had a differentiable function as the solution. Now, it wasn't any more regular than that, but it was at least as regular as the initial data. Everything that we've seen so far up to this point, if we start with something continuous, our solution is going to be continuous. Even when we looked at discontinuous functions for a linear first order PDE, even in that case, the solution was still going to be have the same type of discontinuity or not differentiability. But in this example and the next, we're going to look at situations where we have continuous data here, okay, but our solutions are not going to be continuous, they're going to be discontinuous. And I'll say more about that in the next example as well. Okay, so the example in the example here, I say, as we will see, this will lead to a differential equation for xs prime that is probably impossible to solve analytically. I'd be happy if you proved me wrong about that and were able to solve it. But the point is, oftentimes, when we analyze these differential equations, one of the things that we're most interested in is the location of the shock. So maybe we do some sort of analysis like this, we get a differential equation for the shock location, and then use numerical methods to figure out what the shock location is. And then once we have that, we can use other numerical methods to figure out what the values of the solutions are. Okay. Anyways, so let's just begin as usual. Actually, I'm going to draw the axes. So this is the x-axis, this is the t-axis, and again we're going to have different sets of characteristics. Characteristics emanating from the t-axis and characteristics emanating from the x-axis. And there's going to be a lot of wrinkles in this problem as we go along. At least I see them as wrinkles in this problem as we go along, that you really kind of have to stop and think about things, or at least I did. So again, if we just start, we're going to get t prime of s. Actually, I guess let me work on parameterizing the curve. So I'm going to call it gamma 1. That's going to be the positive t-axis. It's going to be 0 t naught. And gamma 2, that's the positive x-axis. This is going to be x naught 0. So we're going to have t prime of s is equal to the coefficient on the t derivative of u, which is 1. And then we're going to have, what is t of 0 going to be equal to? I'll use the standard colors here. If we start on the t-axis, the positive t-axis, t of 0 is going to be equal to t naught. Whereas if we start on the positive x-axis, t of 0 is going to be equal to 0. I'll just set the eraser on the ground for now. x prime of s is equal to the coefficient on the x derivative, which is z. And I'll step out of the way so you can see this, but it's all the normal stuff so far. And if we start on the positive t-axis, x of 0 is going to be 0. If we start on the positive x-axis, we're going to be at x naught. And then finally, z prime of s is going to be equal to 0. And z of 0 is going to be equal to 1 if we start on the positive t-axis, and it's going to be equal to 1 over 1 plus x naught if we start on the positive x-axis. Okay, so let me do the characteristics for the t equations first, or sorry, not the t equations, well, yeah, the t equations, the one starting from the positive t-axis. Okay, so if we look at that, we're going to get t of s is equal to s plus t naught. So like if this is our representative point t naught, we're looking at the characteristics that start there. X of s is equal to s, and z of s is going to be equal to 1. So these are going to be lines of slope 1 emanating from here. And as always, I'll draw the boundary here with a dashed line. Okay. So now we're going to look at the characteristics that emanate from the x-axis. Now here's where things we have to begin to get a little more careful. Okay, and I'll explain why in just a moment here. So t of s is going to be equal to s. Now for the characteristic that starts at x naught, z is going to be equal to, so z prime is equal to 0, z of 0 is equal to 1 over x naught. So the characteristic that starts here, whatever it looks like, we know on that characteristic, the solution is 1 plus x naught. So x prime of s is equal to z. So x prime, on this characteristic, x prime is equal to 1 over 1 plus x naught. Well, that's a constant as far as x is concerned. And so x of s is going to be s over 1 plus x naught plus x naught. Let me write this a little bit bigger. This is s over 1 plus x naught plus x naught. Okay, so what are these lines going to be? Well, let's first think about the slopes. If I do t prime over x prime, I'm going to have 1 over 1 plus x naught, or just 1 plus x naught. So the slope of these characteristics are going to be 1 plus x naught. So in other words, the slopes get bigger and bigger and bigger as x naught gets bigger. Okay, and actually because of that, I want to move this in a little bit because you'll see why in just a minute. But I want to actually think of a different way to think about this. Because I want to connect it, because all the blue characteristics are up here. So if there's going to be a shock, the intersections have to happen above this blue line here, right? If there's going to be a shock, the intersections have to happen above this blue line, or this blue dashed line. So I'm interested to see where these characteristics, if I look at a characteristic emanating from here, let's say, from there, let's say, I'm interested to see where this characteristic is going to intersect the blue line there. And if I start at x naught, it's going to intersect the blue line here at 1 plus x naught. So I'm going to call this 1 plus x naught. So the blue line, the blue dashed line here is x is equal to t. So if you plug in s is equal to t, and then, so first plug in, for this equation here, plug in s is equal to t. On the blue line, x is equal to t, so you have x equals x over 1 plus x naught, and solve that for x naught, or solve that for x, you get that x is equal to 1 plus x naught. So we're going to have lines, the characteristics are going to look like this. Okay, so that is a straight line, despite what your brain might be telling you, that is a straight line. Okay, so now what's going to happen here as I look at x naughts, they get closer and closer to 0. So let's say this is now 1 plus x naught. This is going to be my characteristic like this, and so on and so forth. what's going to happen is I get closer and closer to 0 as x naught goes to 0. That is, as this goes to the boundary point here, 1 plus x naught goes to 1. So let's call this 1. So if I look at a line very close to this, starts very close to here, the characteristic is going to look like this. Okay, and as this moves closer and closer and closer to the origin, what's going to happen? The purple lines, this purple line is if I imagine taking this and bringing it to the origin, the purple line is going to lie on top of the blue line here. Okay, but notice that the intersection point is going to go to x equals t equals 1, like this. As I bring this there, the intersection point is going to go there. Now, when x naught is literally equal to 0, the purple line is just going to lie on top of the blue line. Okay, but for any positive value of x naught, the intersection point is going to be here at 1, 1. Okay, so what this tells us then, see, because normally in the problems that we've seen so far, there's kind of been this clear wedge of a blue dashed line and a purple dashed line, and we know that within that zone, that's where the intersection, that's where this shock is going to happen. Okay, but here, it's more challenging to figure out when the shock is going to happen, because what happens is that if I draw the limited case here, when x naught is equal to 0, I literally get a line that just lies on top of the blue line. But that's not going to help me figure out when the shock first happens, because for any positive value of x naught, the earliest it can happen, for any positive value of x naught, the earliest any shock could happen is going to be t equals 1. That is when it approaches, when it's equal to that there. Okay, so this is one of the wrinkles in the problem. Okay, so I just wanted you to think about that. And it's probably helpful to sort of graph these in Desmos and then have, a parameter here, I call it a in Desmos when I do something like this, and take a equals to 0. And you're going to see what happens as these lines get closer and closer to 0. If this parameter is never actually equal to 0, you're just going to have lines like this, and they're going to intersect farther and farther down this line, but 1 right here, when x is equal to 1 and t is equal to 1, that's the limiting case. So the earliest the shock can happen here is t is equal to 1. Okay, so again, that's a wrinkle. I want you to think through that. Here's another thing that I'm going to mention when we can sort of determine, a way that we can determine where the first shock location might happen. And it's the following idea. So this is going to involve kind of a few different thoughts, and it might take me a minute to explain. So like from now until the end of when I explain finding the earliest shock time, if you don't want to think about that, or if you didn't follow it very well, don't worry about it so much. Obviously, as always, ask questions on the discussion forums if you have them, but it's just an alternative way of thinking about this. So let's imagine, so this is like some little scratch work over here that I want to go through. So if you think back to calculus, so I'm going to use different letters. Y is equal to f of x. Okay, and let's just think about a very nice function. Y is equal to x squared. So I'm going to graph it. It's going to look like this. Okay, now for any interval that contains 0, this is not an invertible function. For any interval that contains 0, this is not an invertible function. You can go through sort of the multivariable reasoning behind this, but the problem is that the derivative is equal to 0 there, and it curves back up. So at any place where y prime of x is equal to 0, if you look at any x value where y prime of x is equal to 0, it could be the case that in that neighborhood you're not going to be able to invert this function, because those are the only cases where a function can curve back up on itself. Now, if you look at an entire interval and y prime of x is never equal to 0, then on that interval, we know the function is going to be invertible. In the one variable case, how do you think about this? Well, if the derivative is never equal to 0, assuming that the derivative is continuous and stuff like that, if the derivative is never equal to 0, what this means is that the function is either always increasing on that interval or always decreasing on that interval. And so if you have an increasing function, that's an invertible function because it's 1 to 1. If you have a decreasing function, that's an invertible function for the same reason. But it's only going to be on the cases where the derivative is, it's only going to be on the intervals where where you have a point where the derivative is equal to 0 that it might not be invertible. Well, now, just because the derivative is equal to 0 doesn't mean that it is not invertible. For example, x cubed is invertible, but the derivative is 0 there. Okay, so what we want to do is you want to think about this in similar ways. So what does it mean for two shocks to happen? Or what does it mean for a shock to happen? It means that you have two characteristics that intersect at the same time. In other words, if you think about the function for a particular value of t. So if you think about the function, if you think about fixing like s or t as a parameter, and you think about the function that sits x naught to, in this case, 1 over, s over, or if s is equal to t, since it is t over 1 plus x naught, if you think about this function as going from x naught to this over here, we want to know when this fails to be invertible. So in other words, we're going to take the derivative of the x function with respect to x naught, and we're going to set that equal to 0. So if you do that, if you take the derivative of this function with respect to x naught and set it equal to 0, you're going to get that t has to equal 1 plus x naught squared. Okay, so if you fix a value of t, where this derivative is equal to 0, that is, where this function is not going to be invertible, or potentially not going to be invertible for that fixed value of t. So in other words, we're looking at this function for a fixed parameter value of t, x naught going to this right here, okay? Where that function is not going to be invertible is going to be when 1 plus x naught squared is equal to t. Again, we're imagining fixing, right now we're imagining fixing t and finding when the x naught derivative of x is equal to 0, and it's equivalent to this right here. Okay, so now what we want to do is we want to see what is the smallest value of t for which we can make this true. Well, the smallest that x naught can get is 0, which means this is always going to be greater than or equal to 1, which means t has to be greater than or equal to 1. But we note that if x naught is equal to 0, this says t is equal to 1, which says again that the first point, it indicates that the first point of the first time where a shock could happen is going to be when t is equal to 1. And then if we did a second derivative here, you could show that in fact, yes, there is going to be the derivative. We are going to get a convex function or a concave function, whichever one it is. So that in fact, yes, in a neighborhood of in this neighborhood x naught is equal to 0, in this neighborhood we're going to get a non-invertible function. Okay. Anyways, that was a lot. Think through that. I think it's an interesting thing to think about. Think about that in terms of, or talk about it in the discussions if you want to. But let's leave that alone for now. Well, we know what all of this concludes is that our shock happens. Our first shock happens here, or the shock starts when x is equal to 1 and time is equal to 1. So it's only 1 second into whatever this is modeling that the shock happens. This is unlike what we've seen before, where the shock happens at time 0. We have a shock that starts at time t is equal to 1, and the location of the shock is x is equal to 1 as well. Okay, so now I want to see what's going to happen here. So we're going to get some shock that goes up this direction here. So we don't know what it's going to look like, but we know the purple characteristics are in charge to the right, and the blue characteristics are in charge to the left. So the solution is determined by the purple characteristics on the right and the blue characteristics on the left. Now I also just want to mention something about the purple characteristics. The purple characteristics are also going to intersect with each other as well, but they're always going to intersect above the blue line. So if this is x naught and this is x naught prime, they're going to intersect when t is equal to 1 plus x naught times 1 plus x naught prime. Well, remember, this characteristic is going to intersect at 1 plus x naught. This characteristic is going to intersect at 1 plus x naught prime. Prime doesn't mean derivative, it just means another value here. And so t is going to be greater than both 1 plus x naught and 1 plus x naught prime. So yes, these purple characteristics are going to intersect, but they're first going to intersect, each purple characteristic is going to intersect a blue characteristic first. In other words, the shock is going to happen between a blue and a purple characteristic, not between two purple characteristics intersecting. Okay. So now we need to compute. I want to use the RH conditions. So RH for the Burger's equation, if it kind of comes from the standard Burger's equation with f of u equals u squared over 2, this is going to be u to the left plus u to the right over 2. And we know u to the left, that's the blue characteristic, that's going to be 1. Now we just need to figure out what u to the right is going to be. But now u to the right is not going to be constant, so we're going to have to work with u to the right a little bit. So what we know, I'm going to take this like as a representative point here. So I've got xs of t. Okay, so what we know is that along the shock, so along the shock here, we know that, again, I'm going to take this point as a representative point here. We know that, again, taking this as a representative point, you know that xs of t is equal to t over 1 plus x naught plus x naught. Now this is not, I'm not saying this is true for all values of t, okay? What I'm saying is that this shock runs into the characteristic, this characteristic runs into the shock there. That intersection that I just located, xs of t must be equal to this. Okay, because what does it mean for a characteristic to intersect the shock? This is exactly what it means. It means at time t they're equal to each other. So that's what we have here. Now what we know is along the shock, along the characteristic, u is equal to 1 over 1 plus x naught. So I can write this as t times u to the right, and u to the right here really depends on x and t, but I'm not going to write the argument because it's just too cumbersome. And then again, u to the right is equal to 1 over 1 plus x naught, so I can solve that for x naught and get that this is equal to 1 over u to the right minus 1. So I've got xs is equal to this. So I want to replace u to the right with something here. I want to replace u to the right, so I want to solve this equation for ur in terms of xs. Okay, well this becomes a quadratic in the ur variable. There's a typo in the notes here that I need to fix. I'm not exactly sure where it happens at this point, but you get that ur is equal to xs plus 1 plus or minus the square root of xs plus 1 squared minus 4t. In the notes I have plus 4t squared, and then divided by 2t. Okay, now u is a decreasing function of x, so that tells me that I want to take the minus solution. So I'm going to take the minus solution here. So that's what ur is. So I'm going to take this and I'm going to plug it into that equation there. That gives me, that's the Rankine-Hugoniot condition on the left-hand side, and that's going to be the shock velocity. So if I just take this and I copy and paste it up there, I get the following. I get that xs prime xs prime of t is equal to xs plus 1 plus 2t minus the square root of xs plus 1 squared, and it should be minus 4t, it's the same typo there, divided by 2t. Okay, now there's another way to do this. So the way that I kind of talked through this was different than how we talked about it before, but this also is the first case where the right-hand side of the shock, or any side of the shock, the function is not constant there. So another way to do this would just be to take a point. If you look on the right-hand side, and you want to look at ur of xt, this is going to be equal to 1 over 1 plus x naught, and you know that x is equal to t over 1 plus x naught plus x naught. You solve this for x naught, you solve this for x naught in terms of x and t. You plug it in there. You take your UR, you plug it into the Rankine. You take that and plug it in up there, and you're going to get the same thing. You're going to get something that's going to look a little bit different, but I'll let you figure out what algebra. It's going to look a lot different, actually. In fact, it's almost going to look like the inverse of this. So, but I will let you figure out what algebraic manipulations you need to do to get that solution to look like this. Okay, now the point is, at this point, we now need to figure out what this is. So we now need to solve this for excess. I've not thought about it, but I do not think that this is something that can be solved analytically. Again, prove me wrong. That would be great if you could. But at least we now have an ordinary differential equation with a starting location, x of 1 is equal to 1, and we can do some numerical method to solve this to find the shock location for this problem. Okay, that was a long problem. I don't think the next one is probably going to be as long. So, all right, I'll see you guys in a moment.